the computer. Woohoo! Maybe. Okay, looks like there. You guys can see it over there, and I can see it over here. But we're a little sparse over here. All right. So where we finished on Wednesday was with mirrors, and we started doing refraction, and we had talked about the paperweight problem. And the big part about these problems are that you're going to have to account for the index of refraction, and this is going to essentially be for thick lenses or for thick purposes. So in this case, we've got, okay, that's weird, doing weird stuff, whatever. We get the images formed by refraction. So we've got two transparent media, meaning we can shine light through it, and we have the boundary of the surface. So you're going to have to keep track of where your radius of curvature is. And so in this case, we're going to have the object outside the lens or the paperweight, and then have the image on the inside. We're still going to use the P to mean towards the object, and Q to mean towards the image. And in this case, we usually are working with whatever it is, the glass, the water, or whatever it is, as being less than the air. So typically this is how we end up working with it. And so when you have to account for that, we're going to do something very similar to what we did with mirrors, except now we have to account for the fact that we've got the two differences of indexes of refraction. So we end up having to put in our index of refraction over where the object is, our index of refraction over where the image is, and then we're going to get the differences of the two divided by R. So I'm going to sneeze. Excuse me. So we end up getting this relationship that accounts for those indexes of refraction. Maybe. Okay. So the side of the surface where the light rays originate is defined as the front. The other side is the back. And real images are going to be formed on the back of the surface. So if we are thinking about that definition of could I put a piece of paper there, if I could fit the piece of paper in my glass, I would actually have it shine on a screen. So it makes it real. And because of the sign conventions, the refracting surfaces are opposite of the reflecting surfaces. So you got to kind of keep track of that. In fact, oh, no wonder I'm having weird things happen. There we go. Now it will behave. So if I look at my sign conventions for refracting surfaces, I'm going to have the positive when the object is in front of the surface, or it's negative when my object is in the back of the surface. So if I'm doing the paperweight problem and my object is in the paperweight, I'm going to have a negative value. So when you're working that paperweight problem, you're going to get that negative value. The image location is going to be positive if it's behind the back of the surface, but if my image is outside of my paperweight, it's going to be negative. So you can see why I said keeping track of the sign conventions becomes really important, because you're going to end up having that sign convention. The same is going to be the same case as what we've had before. If it's upright, it's going to be positive. If it's inverted, it's going to be negative. And then my radius of curvature can go either way. And the traditional way we look at it, let me go backwards. The traditional way we look at this is going to be a positive radius of curvature. And if I had it going this way, it becomes a negative radius of curvature. Okay, negative radius of curvature. So you get a little bit different aspect. So we start working at it. So if I have flat refracting surfaces, I do get a little bit of a difference because I have to account for the fact that this doesn't have a radius of curvature at all. And we end up with this being the sign. And we get R being infinite. So we know what that's going to, we end up getting that really strange result. But the thing about that is we're going to get a virtual image formed. So just like the one with my square cube that you guys saw, that's what happens. Even so, if I have the object at the bottom, my image is ultimately going to show up somewhere inside my cube. But the sign conventions are the same. Now the whole idea behind this is that's the paperweight problem. But ultimately, we're trying to get to a lens problem. And we can have thick lenses or thin lenses, and ultimately we're going to work with thin lenses. But we can get these lenses that we have come in, so I can have two radiuses of curvature. I can have the radius of curvature in the front, and I can have the radius of curvature in the back. And so what you end up having to do is we get the radius of curvature in the lens in the front, the object reaches first, and then we get it back to go back and forth. So you get these weird things coming into play, but the idea is we're going to ultimately get to rearranging the equation, and then you will get to what we know as the lens maker's equation. So the lens maker's equation is when I'm going to have my object distance plus my image distance, the difference in the index of refraction and error, and then the two radiuses of curvature is going to give me the focus for my thick lens. So when I'm making eyeglasses, this is exactly what we end up with. And we have to account for this when we're making eyeglasses, because if you've ever gone from crown glass or optical glass to the polycarbonate, which is most of what our eyeglasses are made out of now, that's what they have to account for in order to get the focus, because the material is going to make a bit of a difference. So this is the lens maker equation. So far, if I'm making up my cheat sheet for the final, I'm making sure I have my wave equation, C is equal to lambda times the frequency. I'm making sure I have my sign conventions. I'm making sure I have my mirror equation. I'm making sure I have this lens maker equation. And then you're about to get the thin lens equation as well. So that's the lens maker's equation. So my images, now when we get our lens thin enough that we can neglect the thickness of the lens. And that's what's going to allow us to represent our lens with a straight line when we do our optical ray diagrams. We'll end up being able to omit those lenses. And this gives us the thin lens equation. So we can get rid of those radiuses of curvature. We get rid of all of that stuff when I have a small enough thickness of the lens that I don't have to mess with it. And that gives us what we call the thin lens equation. Now, this is one way you see the thin lens equation. I'm going to show you the other way you see the thin lens equation, because we write it a little differently for different situations. So I'm going to switch this over. Let's see if it works. It wasn't working this morning. All right. So there's my thin lens equation. Okay. There it is. So first thing I'm going to do is I'm going to get a common denominator. So I'm going to get Q plus P is PQ is equal to 1 over F. So all I did was rewrite this so that I got a common denominator. I'm going to flip it so that I get the focus is going to equal PQ Q plus P. So a lot of books, you'll actually see it written that way versus written as 1 over P plus 1 over Q is equal to 1 over F. And then you'll also see it written, you'll also see it solving for Q, and you'll also see it solved for P. So it's just a matter of what your problem is and how you want to work the problem. Depends on which way you want to have it on your cheat sheet, because this is what it's going to end up working to give you. So it's a nice way to rearrange your equations so that you have the information just the way you want it. And it's also easier for you to work with down the way. So that's our lovely thin lens equation. So a couple things, because light can travel through either direction of the lens ultimately has 2 focal points. Luckily for us, most of the time we don't worry about it because we actually design the lens to not have that. So one focal point is for light passing one direction and one is for the other. But however, there's only one focal length and each focal point is the same distance from the lens. So when we design our lenses, we get that piece. So my focal point for a converging lens, so I'm going to get a flat side here and my converging lens. I get parallel rays that come in. This is my focus. Same way from over here. So the parallel rays pass through the lens and they converge at the focal point, and the rays can come from the left or from the right. Now, diverging lenses, I'm going to spread the rays out. And my focal point for the diverging lens is going to be a little different. So the focal point is where the rays appear to have originated. So we get converging lenses and diverging lenses. So when I do my sign conventions, the front or virtual side of the lens is going to have a positive P and negative Q, or the back or the real side is going to have a negative P and a positive Q. And this sign convention works whether it's a converging lens or a diverging lens. So it's going to work either way. You guys are madly writing, so I'm going to wait. Okay, we're good? All right. So another way of looking at it is I'm going to be positive when the object is in front of the lens with a real object, and the object is in the back of the lens, it's going to be negative. If I get my image in the back of the lens, it's a real image. I'll actually be able to put a piece of paper there and actually see it. The image is in front of the lens, it's a virtual image. I still get my image heights. If I get that, it's going to be upright or inverted. And then I have my 2 radiuses of curvature if I need them, and my focal length to go forward there for a converging or a diverging lens. So if I'm told I have a diverging lens, this is the critical thing you got to look at. So if I'm given a problem, it'll say you have a converging lens or a diverging lens. And that immediately is going to tell you whether I have a positive focus or I have a negative focus. And that's usually where you get your uh-ohs, that they don't quite match up for what you're doing. don't quite match up for what you're doing. Then I still have the same magnification. We've seen this magnification equation before. It's going to look the same. If I get a negative, it's going to be inverted. So I have different shapes. So converging lenses can be like this. They can be our bioconvex, our convex concave, or our plano-convex. The trick for these is look at the middle versus the end. So here the middle is fattest and the end is narrowest. So the middle is fattest and the middle is fattest. So if I'm ever given a handful of lenses, I can just look at my lenses to be able to tell which way these are going to go. Are they converging or diverging by looking at how those pieces are there. So these are converging lenses. My diverging lenses, my middle is narrower than the end. And remember, diverging lens is going to spread the real rays out instead of a converging lens where it's going to try to put it at that focus. And on a diverging lens, I'm going to have to look at where the rays of light appear to have originated. And so these are really thin at the middle, and they're thick at the end. So when we're going to do these problems, this is the methodology. We're going to use 3 rays. The first ray is drawn parallel to the principal axis, and it's going to go to my mark for my lens. And then where my mark of my lens is, it's going to pass through the focus. And I've got a picture of this here in just a second. The second one is drawn through the center of the lens and continues in a straight line. Remember, 2 lines or 2 points make a line. So one point will be the top of my object. The other point will be where the principal axis bisects the lens. And then the third one is a ray drawn through the focal point on the front of the lens as if it's coming back and goes back to the principal axis. But it only takes 2 of these to find the image, and the third one is a check. So basically what it's telling you is, here's our first ray. I'm going to draw parallel to the principal axis and then through the focal point. I'll do the second one through the principal axis and back. I'll do this one will go through the focal point, and then I'm going to be parallel to the principal axis. So 2 of these will help define the image. The third one is a check. And in this case, if my object is outside of the focal point, I'm going to get the image is going to be real. So I can put a piece of paper there and I can actually see it. It's going to be inverted from the original, and the image will be on the back side of the lens. So I'm going to be able to come through and then be on the back side of the lens. Now, if my object is in the first part, I still follow the same rules. I'm going to take this one that goes through the principal axis. I'm going to be parallel and go through the focus. But what you see happen here is, because I'm not going to get these rays to intersect in the back, I'm going to have to extend to where these appear to be coming from. So I end up drawing my line a little bigger. Once I get this one, I'm going to extend it back and I'm going to draw my line to get it bigger. And I'll end up with the image on the same side of the lens as my object. This becomes, because if I have these dashed lines here, that tells me I have a virtual image. Because if I put my screen up, this isn't going to show up. The image turns out to be upright. And the other thing that we didn't talk about is the magnification. In this case, it looks like this is going to be the same height, and I don't get a magnification at all. But look what happens when I go through here. I do get a magnification. My image actually gets bigger than my object. My image actually gets bigger than my object. And the key here is that you can represent your lens with a straight line right down the middle. So if I'm doing it, if I'm drawing it, I can use it on my piece of paper, and I can draw this to scale. And if I use my paper, I can really draw it to scale. If my object is 1 centimeter high and I am 3 centimeters away, I can draw this and have it be to scale on my piece of paper. So you can use a ruler to figure this out rather than doing the calculation. So if I have a diverging lens, I'm going to follow a very similar aspect. There's my image or my object. I'm going to go right through the lens. Right through the lens. I have one that goes through the focus. And I have my parallel that goes through the focus as well. Again, I can use 2 to define where my image is, and then I can use the third one to check it. The image is going to be virtual. The image will be upright. The image will be smaller, and the image will be on the front side of the lens. And so you can really, when you get to ray optics, you can draw all of these things and really work them out. So for images, our summary is that for converging lenses, when the object distance is greater than the focal length, the image is going to be real and inverted. If I've got a converging lens where I put the object inside the focal length, it's going to be virtual and it's going to be upright. And for diverging lenses, it's always virtual and it's always upright. So if on the test, I'm asking you to describe the image or give me the characteristics of the image, you may be looking at what's the size, you may be looking at just this part of the information, you may be actually looking at the calculation depending on what we end up having. Now, we can force things to do weird things, and that's what the Fresnel lens does. And refraction occurs only at the surfaces of the lens, so we can use a Fresnel lens and build a lens that we can get a very powerful lens without using an incredible thickness of the glass. So that's kind of a neat way to look at it. So Fresnel lenses are fun. Now we get to the tricky stuff. This is where we put lenses in combination with each other and lenses in combination with the mirrors. So what we do when we take combinations of lenses, you start with where the object is, and then you do where the image is going to be for that lens. And once you've got that image becomes the object for the second lens or the mirror. Okay, so let me go through that again. I start out with my object and I draw my diagram for the first lens, figure out where my image will be, and then my image becomes the object for the second lens. And if I do this for mirrors or everything, and I repeat that sequence in order to get there. So I can have 2 lenses in contact, or I can have 2 lenses there. So let's look at the example. So I start with this object, use my rules to find my image. This becomes the image. Then so now I'm going to be inside the focal length of this lens given how far apart they are. I'm going to be inside that. I do the same arithmetic and everything that I need to find my object for this one based on this is where my image is, and my ultimate object